Hello students, in this lecture we will study about the drift velocity and the drift current. So let me start with this numerical. If the drift velocity Vd is 5 meter per second in the field 100 volt per meter, then calculate mobility. So the expression for drift velocity, it is mobility times of electric field mu e. Basically, what is drift velocity? When we apply electric field in a conductor, suppose this is a metal, or we can say it is a conductor, and we apply the voltage across this metal, then the electrons in the metal starts moving. Okay, then the velocity acquired by the average velocity acquired by the electrons available in the metal is called as drift velocity. And the drift velocity, it is given in this question, is 5, and it is mu into electric field is given 100. So the value of mobility, it is 0.05 meter square per volt second. So this is our required answer for this question. Okay, so let me understand the next question. What is the diffusion constant D at a room temperature if charge carrier mobility is 0.4 meter square per volt second? In this question, mu is given. In this question, mu is given. It is 0.4 meter square per volt second, and according to Einstein's relationship, it is d by mu, it is equal to constant. Diffusion constant by mobility, it is equal to Vt, and Vt is a thermal. Vt is a thermal voltage. So the value of diffusion constant is mobility times of thermal voltage. Mobility is given 0.4 and thermal voltage is 26 millivolt. So it is the value is 0.0104 meter square per volt second. So from this question, we should know that the d by mu ratio is constant. D is diffusion constant and mu is the mobility, and their ratio is constant for semiconductor. For n-type semiconductor, it is dn by mu n. For p-type semiconductor, it is dp by mu p, and this value is Vt, right, and which is equal to Kt by Q, right? So this is called as Einstein's relationship for the semiconductors, right? So from here we will calculate the value of diffusion constant D. Next question is the minority carrier lifetime and the diffusion constant in the semiconductor is 100 microsecond and 100 centimeter square per second. Then calculate diffusion length. Okay, so tau is given 100 microsecond and diffusion constant dn, it is given 100 centimeter square per second. So the diffusion length, the formula of the diffusion length is L is equal to under root of d into tau, and we will calculate. So the value of L, it is 0.1 centimeter. Okay, so L is the diffusion length, and the simple expression for L, it is under root of d into tau. A sample of n-type semiconductor has electron density of 6.25 into 10 to the power 18 per centimeter cube at 300 Kelvin. If intrinsic concentration Ni, it is 2.5 into 10 to the power 13 per centimeter cube, then calculate hole concentration. So this question is given, and this question is based on the mass action law, which is equal to Np is equal to Ni square. So mass action law basically is calculated minority carrier concentration. So mass action law mainly used to calculate minority carrier concentration, minority carrier concentration in the extrinsic semiconductor. So the value of hole concentration, it is Ni square by n, and it is equal to 10 to the power 8 per centimeter cube. We'll put this value of Ni is given, it is 2.5 into 10 to the power 13 square, and divided by n, it is 6.25 into 10 to the power 18. So the next question is aluminum strip with resistivity of 3.44 into 10 to the power minus 8 ohm meter, and cross section area is 2 into 10 to the power minus 4 millimeter square, and length is 5 millimeter. Then find the voltage drop across aluminum strip if 50 milliampere current is passing through it. So we will simply use here V is equal to IR, right? But resistance for the aluminum strip in this case, it is rho L by A. Resistivity rho into length divided by area. So we will calculate, we will put all the values where resistivity is given 3.44 into 10 raised to power minus 8. Length is 5 and area is 2 into 10 raised to power minus 4, and we will just put this value here. Current is given, it is 50 milliampere. So we'll get the voltage. So the voltage is here 43 millivolt. And the next question is, a semiconductor wafer is 0.5 millimeter thick. A potential of 100 millivolt is applied across its thickness. What is electron drift velocity if mobility is 0.2 meter square per volt second? and how much time is required for an electron to move across its thickness. So electric field is voltage. This is voltage divided by, this is a thickness. It's a thickness, right? It's a thickness, right? So 100 millivolt divided by thickness is given, which is 0.5 millimeter, and this value is 200 volt per meter, right? Electric field is just, we will calculate voltage divided by thickness. So the drift velocity, this is Vd is drift velocity. It is mobility times of electric field. So mobility is given 0.2 and electric field is 200. So this is 40 meter per second. This is drift velocity, and we want to calculate the time required. So drift velocity, it is distance upon time here, right? So 0.5 millimeter, it is the thickness divided by time, and it is the velocity. Velocity is 40 meter per second. Then time required is 12.5 microsecond. A small concentration of minority carriers is injected into semiconductor at any point, and electric field is 10 volt per centimeter is applied across the crystal. So minority carriers travels 1 centimeter distance in 20 microsecond. Then calculate mobility mu in centimeter square per volt second. So drift velocity here, it is 1 centimeter by 20 microsecond. It's a given, right? 1 centimeter is the length, and it is covered in 20 microseconds. So drift velocity is 1 centimeter by 20 microsecond, and we can calculate Vd. It is equal to mobility times of electric field. So we can calculate mobility from this expression, and this value is 5000 centimeter square per volt second. And the next question is, in the germanium, leakage current is 5 microampere at 10 degree centigrade. Then find the leakage current at 25 degree centigrade. Leakage current flows to minority charge carriers, and it is the function of temperature, right? And I naught of T2, it is equal to I naught of T1 into 2 to the power T2 minus T1 by 10. So T2 minus T1 is given here 15. So it is 5 microampere into 2 to the power 15 by 10, and it is equal to 14.14 microampere. So leakage current at temperature T2, right? It is 14.14 microampere. It increases with the temperature. The diffusion constant of holes in the silicon is 13 centimeter square per second. Then what is the diffusion current if concentration gradient dP over dx is minus 2 into 10 to the power 14 holes per centimeter cube per centimeter, and area is 1 centimeter square. So here this value, the diffusion constant for holes, it is dP, right? And dP over dx is given here, and area is given 1 centimeter square. Okay, So diffusion current density for holes, the formula of this, it is minus of q into dp over dx. So this is the density, this is the diffusion current density, and this is minus of 1.6 into 10 raised to power minus of 19 into dp. It is given 13 centimeter square per second, and dp over dx is given minus 2 into 10 raised to power 14. So this is given 0.416 milliampere per centimeter square. So this is our required answer. And we are asked to find out the value of current. So current is current density into area. So current density is 0.416 into area is given 1. So this answer is 0.416 milliampere. This is our required answer. So the next question is the silicon sample with unit cross sectional area given at the thermal equilibrium, and mu n is given 1350 centimeters square per volt second. Thermal voltage is given 26 millivolt, right? Then calculate magnitude of electric field at x is equal to 0.5 micrometer. Here it is given x is equal to 0 micrometer, and here it is given x is equal to 1 micrometer, and here it is x is equal to 0.5 micrometer. So conductivity conductivity is nq mu n. It is an n type of semiconductor, and in the n type of semiconductor, n is approximately equal to nd. So we will put here n is approximately equal to nd. This is a graph of voltage versus x, right? At 0.5 micrometer, the voltage will be 0.5 volt. At 1 micrometer, the voltage will be 1 volt. So electric field is 1 volt per micrometer, right? And this is 1 into 10 to the power 6 volt per meter. Okay, so this is electric field, right? Now question is calculate current density at x is equal to 0.5 micrometer. So we know that drift current density, right, it is sigma into E. So we will put here sigma value is nq mu n into E. Sigma is nq mu, so nq mu into E. The value of concentration of electrons, it is 10 to the power 16 into 1.6 into 10 raised to power minus 19. Mobility is 1350, and electric field is 10 to the power 4. So we can calculate here the value of current density, which is 2.16 into 10 raised to power 4 ampere per centimeter. Let me solve the next question. In a semiconductor at room temperature, intrinsic concentration is given. It is 1.5 into 10 raised to power 16 per meter cube. And the resistivity is given 2 into 10 cube ohm meter. It is converted into extrinsic semiconductor with the doping concentration of 10 to the power 20 per meter cube. For the extrinsic semiconductor, right, we have to calculate minority carrier concentration, mobility, resistivity. Here we have to assume mu n equal to Vp. Although mu n is always greater than mu p, As usual, mu n is greater than mu p, but in this question we will assume here mu n is equal to mu p, right? It's given in the question. So mass action law, minority carrier concentration, it is Ni square divided by majority carrier concentration. So Ni square, it is 1.5 into 10 to the power 16 whole square by majority carrier concentration, it is 10 to the power 20. So this answer is here 2.25 into 10 to the power 12 per meter cube. Intrinsic resistivity, it is equal to reciprocal of intrinsic conductivity. So it is 1 over Ni cube into mu n plus mu p. So intrinsic resistivity, it is 2 into 10 cube, and it is equal to 1 upon Ni. Ni is 1.5 into 10 to the power 16 into charge, it is 1.6 into 10 to the power minus 19 into twice mu n, since it is given in this question 0.55 meter square per volt second. Now the resistivity, it is 1 upon conductivity of extrinsic semiconductor, and the conductivity of extrinsic semiconductor, it is n mu. N is given 10 to the power 20, Q is given 1.6 into 10 to the power minus 19, and mu is given 0.55. So we'll put this value at in the expression of rho, right? So we will get the resistivity. So the next question is given: a semiconductor silicon is doped with donor impurities to the extent of 1:10 to the power 7. Then calculate first part, it is a donor concentration. Electron and hole concentration in the doped semiconductor and conductivity and resistivity of doped semiconductor. And one more thing, one more question is asked: how many times? Conductivity is increased. In the semiconductor. Because of doping. Okay, so here some parameters are given, like total number of atoms. It is given 4.42 into 10 to the power 22 per centimeter cube. Intrinsic concentration Ni, it is 2.5 into 10 to the power 13 per centimeter cube. Electron mobility mu n, it is 3800 centimeter square per volt second. And mu p, it is given 1800 centimeter square per volt second. So the electron concentration, it is approximately equal to Nd, because it is of n-type semiconductor. So n is approximately equal to Nd, and this value is given 4.42 into 10 to the power 22 into 1 is to 10 to the power 7. And this value is 4.42 into 10 to the power 15 per centimeter cube. So the whole concentration P, it is equal to Ni square by n. Ni is given 2.5 into 10 to the power 13 whole square by n. So it is 6.25 into 10 to the power 26 divided by n, it is 4.42 into 10 to the power 15, right? So the whole concentration, it is equal to 1.414 into 10 to the power 11 per centimeter cube. So this is our first part, this question. Okay, then conductivity which is equal to sigma n, it is n q mu n. N is given 4.42 into 10 to the power 15 . 2.6873. So this value is conductivity of n-type semiconductor. So the resistivity of n-type semiconductor, it is 1 over sigma n and it is 0.373 ohm centimeter. So the next question is how many times the conductivity will increase because of doping. So we have to calculate first intrinsic conductivity, and intrinsic conductivity, it is Niq mu n plus mu p. Ni is given, it is 2.5 into 10 to the power 13. Mu n plus mu p, it is 3800 plus 1800. So we will calculate sigma I, it is 0.0224 mho per centimeter. And question is asked how many times the conductivity will increase. So the factor at which the conductivity will increase, it is it is 2.6873 by 0.0224, and this answer is 120 times. So 120 times the conductivity will increase because of doping. A semiconductor is doped with acceptor impurities. To the extent of 4 impurity atoms for every 1 million of atom. Then find conductivity. Right? So the total number of atoms in the silicon, it is given 5 into 10 to the power 22 per centimeter cube. And intrinsic concentration, it is 1.5 into 10 to the power 10 per centimeter cube. And mu n, which is electron mobility, it is given 1300 centimeter square per volt second, and hole mobility is given 500 centimeter square per volt second. So Na, which is acceptor acceptor ion concentration, it is 5 into 10 to the power 22 into 4 is to 10 to the power 6, right? So this answer is 20 into 10 to the power 16 per centimeter cube. So conductivity, it is sigma, right? It is Na cube. So the next question is given: a semiconductor which is of silicon is doped with donor impurities. To the extent of 1 is to 10 to the power 6. Then calculate, the first point is conductivity due to majority carriers. Second point is conductivity due to minority carriers. It's given acceptor ion concentration Na. It is 5 into 10 to the power 16 per centimeter cube. So conductivity to conductivity, I'm sorry, this is Nd. Conductivity due to majority carriers is Ndq into mu n. Nd is given 5 into 10 to the power 16 into mu n. It is given 1300. And this answer is 10 to 10.4 mho per centimeter. And conductivity due to minority charge carriers, it is PQ mu P. This is equal to Ni square by N Q mu P. So when we calculate this Ni square by N quantity, so this is 4500 into mu P. Mu P is given here 500. So this answer is 3.6 into 10 to the power minus of 13. So this is our required answer. So this is the question, right? Semiconductor, which is silicon, is doped with donor impurities to the extent of 1 is to 10 to the power 7. We have to calculate donor concentration and electron and hole concentration in the doped semiconductor. Conductivity and resistivity of the doped semiconductor, and how many times the conductivity is increased in the semiconductor because of doping. Okay, let me explain it. Total number of atoms is given, it is 4.42 into 10 to the power 22 per centimeter cube. Intrinsic concentration, it is 2.5 into 10 to the power 13 per centimeter cube. And mu n, it is the mobility of electron, it is 3800 centimeter square per volt second. Mu p is 1800 centimeter square per volt second. The electron concentration is approximately equal to Nd because it is an n-type semiconductor, and this is 4.42 into 10 to the power 22 into 1 is to 10 to the power 7, and this answer is 4.42 into 10 to the power 15 per centimeter cube. So the whole concentration, it is Ni square by N, it is 2.5 into 10 to the power 13 square by N, electron concentration, and this is due to the mass action law. So according to this mass action law, it is the whole concentration, it is 1.414 into 10 to the power 11 per centimeter cube. So sigma n, which is a conductivity of the n-type semiconductor, it is n q mu n, and this answer is 4.42 into 10 to the power 15 into charge. Charge is 1.6 into 10 to the power minus 19, and mu n is 3800. It is given. So we will calculate the value of sigma n from here, and this is 2.6873 mho per centimeter. And the value of resistivity, it is 1 hour sigma n, it is 0.373. We will just take reciprocal of it, and this is the answer, 0.373 ohm centimeter. Intrinsic conductivity is Niq into mu n plus mu p. So this we can calculate. Ni is the intrinsic concentration, Q is the charge, and mu n and mu p. We will take this, the sum is, and the answer is 0.0224 mho per centimeter. And question is in how many times the conductivity will increase due to doping. So we'll just take the ratio. This is the conductivity after doping, and this is the conductivity before doping. When you will take the ratio, then this ratio is 120 times. And the next question is, a semiconductor which is a silicon is doped with acceptor impurities to the extent of 4 impurity atoms for every 1 million of atom. Then find the conductivity. And it's also given total number of atoms are 5 into 10 to the power 22 per centimeter cube. So the intrinsic concentration, it is 1.5 into 10 to the power 10 per centimeter cube. Mu n, it is 1300 centimeter square per volt second. Mu p, it is 500 centimeter square per volt second. So Na, it is acceptor ion concentration, it is 5 into 10 to the power 22 and 4 is to 10 to the power 6. This is given doping concentration. So this answer is 20 into 10 to the power 16 per centimeter cube. So sigma, it is Na q mu p, right? So the value of Na, it is 20 into 10 to the power 16. Q is 1.6 into 10 to the power minus 19 and mu p is 500. So we will calculate the value of sigma. It is 16 mho per centimeter. A semiconductor which is of silicon is doped with donor impurities to the extent of 1 is to 10 to the power 6. Then calculate conductivity due to majority carriers and conductivity due to minority carriers. Given Nd, it is 5 into 10 raised to power 16 per centimeter cube. So conductivity due to majority charge carriers is Nd q mu n. Nd is 5 into 10 raised to power 16. Q is a charge, it is 1.6 into 10 raised to power minus of 19 and the mobility is 1300, right? So we'll calculate the conductivity of majority charge carriers, which is 10.4 mho per centimeter. So the conductivity due to minority charge carriers, it is pq mu p. It is Ni square. P is the Ni square by n and q is the charge and this is mu p. Mu p is the mobility of holes, right? This we have written from the mass action law. Mass action law is Np is equal to Ni square, right? So we have calculated P, which is equal to Ni square by n. So this we will calculate. Then this answer is 4500 into charge is 1.6 into 10 raised to power minus 19 and mu p, it is 500. So this is our required answer for conductivity due to minority charge carriers.